So we keep learning integration techniques, and the next method that we're going to learn is called integration by parts. Okay, so say that you're given the task, somebody asks you to take the integral of x cos x dx, and we know that the substitution probably method won't work here because this is really not a combination of a function and its derivative. So this is a prime example of when integration by parts is going to be helpful. Let's say that you're also given the clue that you are looking at part of a product rule that was done. So that's a huge clue. So this is a little bit like you're Sherlock Holmes and you're looking at a crime scene that happened and you're trying to figure out exactly what happened, only seeing a part of the results of an event. And this is essentially what integration by parts is going to involve. There was a product rule that happened and we're seeing part of it, and we're going to try to reconstruct everything that went on. So here's Benedict Cumberbatch. He's concentrating very hard. You can tell right here, and he is Sherlock Holmes. He's looking very intently at this. We are going to now reconstruct what possibly happened with some sort of product rule occurring. So say that there was some product, something times something, and we took the derivative of it. We remember that product rule says, okay, if you're taking the derivative of a product, you can take like the normal first times the derivative of the second plus the derivative of the first times just regular second. So we have, these essentially four pieces in the product rule. Let's say that this guy right here was a part of that. So maybe we ended up with an x cos x plus something else. Could we reconstruct a possibility for what might have happened here and here? So let's start here. What's something that would be here and here that could have resulted in part of its derivative being this? It is possible that we had something like an x times a sine x, because then the x would just be regular and the sine x, the derivative of that would be cosine x. If this was the case, then what would go here? Well, at this point we would take the derivative of this and then just regular that. The derivative of x is 1, and then regular sine x is just sine x. Okay, so this is a plausible event that could have occurred that would have resulted in this being part of a product rule. Now, this is where the integration by parts technique comes in and is super helpful, is we say, okay, this product rule was done, now reverse it. Now take the antiderivative of everything on the left side and the right side. So take the antiderivative of everything. Well, if we take the antiderivative, so let's say take the antiderivative of both sides. And on the left side, we'll get just x sine x, right? The antiderivative of the derivative is just the original product. Now, on the right side, we'll end up with some integrals. The antiderivative of x cos x is the integral of x cos x dx. And then we have an integral of sine x dx. At first, this doesn't look super helpful. It looks like we've just traded one sort of complicated thing for another, but remembering that this was our task, we needed to find the integral of this. The integral of that is actually sitting right here. And it's equal, if we move to this guy over to the other side, this integral is equal to this minus this integral. And so you think again, why is that helpful? I mean, we still have integrals in the problem, but this is done. This is like evaluated, and this integral is actually a simpler integral than what we started with. So this integration by parts has told us that x cos x dx is actually equal to x sine x minus the integral of sine x dx, which is x sine x minus, let's see, the integral of sine x will be a negative cos x, so plus cos x plus RC. And we have found the integral that we're looking for. So this is essentially integration by parts. We are going to, in looking for an integral, we're going to deconstruct a possible product rule and hopefully find an integral that is simpler to evaluate. And that will lead to the result of the original integral that we were trying to find. So now we're going to generalize what we just did. So this is the product rule from back when we were younger. We learned it in Calc 1. And what we're going to do is we're going to anti-differentiate both sides, the left side and the right side, and move a few things around. And then we're going to find an integral for this guy right here. So this is one way that we will see integration by parts. I've just taken the antiderivative of both sides here, and this becomes this. This guy I moved over to the other side, and we get this. A lot of things that we learn in calculus, this can be written in different ways, and different textbooks will write it in different ways. The textbook we're using is going to write it a little bit differently, and it's a little bit cleaner, and so I'll show you what that looks like. Here, instead of using f's and g's, we're going to use u's and v's. And the integral of u dv, this is like a task that you're given, an integral to evaluate, will always equal uv minus the integral of v du. And we're remembering that all of this just comes from a reversal of the product rule. So when we're given an integral to evaluate and we think that integration by parts might be a good fit, the first thing that we have to decide is we have to choose which part we're going to let equal u and which part we want to let equal dv. And so the integral will have some sort of product in it already. Otherwise, this method won't apply. And we have to choose something to be the u, and then the rest of it needs to be dv. And as you practice, you'll become more skilled at doing this, but a few tips are, we really want u to hopefully get simpler as you differentiate it. So we want u hopefully to get simpler as we differentiate it. And very importantly, at some point we're going to have to find the integral of v du. We traded this integral for this integral, so we really want this one to actually be simpler than this one. Otherwise, the method won't work. It makes something more complicated. So we need the integral of v du. It needs to be a little easier. So that's the hope, to integrate. And this is a real key to using this method. So both of these are pretty helpful, but this one on the right is sort of essential, that we find an integral that's easier to integrate. So this part is our task here. This guy should be a relative piece of cake. You are going to have to do kind of a mini integration in here. After you decide what dv is, you're going to have to anti-differentiate that to get v, but you've chosen dv in order to make that a little bit easier. So we'll say piece of cake mostly. It depends on how we choose things. And then this guy here, this is where we want it to be easier than the original integral. So please be easier. All right, great. Let's get some practice with this method. So say that we're asked to integrate e to the x halves times x dx. And I look at it, the u substitution method probably won't work because I don't see a derivative pair here. So we're going to give integration by parts a try. And so our first job is really to decide what we want u to equal and what we want dv to equal. And we may not make the right choice the first time. That's okay. I mean, we're going to try different things, but remembering that we want u hopefully to get simpler as we differentiate it, and keeping in mind that whatever v du is, we do need to be able to integrate that. So I have a few choices. I mean, this is definitely as a product, and it's kind of naturally split up into e to the x halves and an x. So one of these is going to be u, and one of them is going to be dv. The u, I'm going to choose it to be x, because I do believe that this will get simpler as I go. So we'll let this equal x, and then what's left over is e to the x halves dx. And so I can see that I have to be able to anti-differentiate this, so go backwards, and I look at e to the x halves, and it'll be e to the x halves, probably times 2. So just thinking through that, if I took the derivative of this, it would be 2 times e to the x halves times a half, and that does give me this as its derivative. This one's nice. Du will just equal 1 times dx. And then I'm going to invoke this integration by parts rule. I was given an integral of u dv, and because of this rule, I know that that's equal to just u times v. So that's these multiplied together minus the integral of v du. And so this integral here, a combination of these two things, I can already see that it's going to be simpler because it's just got a constant, and then e to the x halves will be easy to integrate. So I think we're in good shape. The original integral now equals 2 times x times e to the x halves, that's the uv, minus the integral of 2e to the x halves dx. Things are simpler. This is done, and this integral I can figure out. So this will equal 2x, let's see, let's move some things out of the way here. 2x e to the x halves, that first part, minus the integral, 2 times the integral e to the x halves, and the integral of e to the x halves is e to the x halves times 2 plus a constant, and 2 times 2 will just be 4. So that's it, we've found this integral. Now in this example, we're going to integrate natural log of x dx, and when you first look at it, you think, what, the product rule doesn't really seem to apply here. And for sure, use substitution wouldn't work here. But we are going to forge ahead and try integration by parts, and you'll see we use it in a sort of unique way. So first job is to choose something for u and dv, and we know that in the end we want dv to be something that we can easily just look at and integrate. This we're hoping will kind of go away or get easier somehow. And we're also going to remember that what the integration by parts looks like. Okay, so this is our reminder of what integration by parts looks like, and what we're going to do is we're going to say, okay, we really only have the natural log of x, so that's going to be our u, and then dx is going to be our dv. So we'll say u is natural log x, and dv is just going to be dx. Then du will be the derivative of natural log of x, or 1 over x dx, and dv is going to be the antiderivative of essentially 1 times dx, and so that will be x. Okay, we have all the pieces. Let's put it together, and we'll hope that something falls out that is easier to integrate than what we started with. So this right here is going to equal v times u, or u times v, and that is just x natural log of x minus the integral of v du. So x times 1 over x dx, and this will be easier to integrate because this x and 1 over x combine in a special way. So that's x times 1 over x dx, and that simplifies to x natural log x minus the integral of 1 times dx, and so that's just x natural log of x minus the antiderivative of 1 times dx is just x plus our constant. Awesome. Okay, so for another example, okay, so this time we're going to find the integral of t squared times e to the t dt, and we can see a pretty natural product here. We just need to decide what u is going to equal, and then what dv is going to equal. And again, u, we want something that hopefully will at least eventually go away, and dv, we need to choose something that we can easily find the antiderivative of. Either of these we could easily find the antiderivative of. E to the t is something that's just not going to really get any simpler or go away, so we probably, let's try t squared for u, and then e to the t for dv. T squared, and then e to the t dt here. And then du is going to equal 2t dt, and v will equal just e to the t again. Okay, so using our integration by parts little reminder up here, we know that this integral here will equal u times v, so e to the t squared minus the integral of 2t e to the t dt. Okay, so for the first time we came across this integral is not one that I can just look at and say what the antiderivative is, but interestingly, I could actually do integration by parts again on this and probably get it to a point where I could just read off the integral. So we're going to do integration by parts one more time. That's something that just sometimes happens, that you have to do it again. And we'll do it just for this part here. All of these things stay the same. And for that part, u, we have to pick our u again, and we have to pick our dv again. So take a minute and think about what you would choose for u and dv. And we're going to pick t to be the u, because that actually will go, when we take the derivative, it'll just turn into a 1 dt, and that's super nice. And the dv then can be e to the t dt. And so the antiderivative is just e to the t. We can see that when we evaluate this part, it's going to be this product here minus the integral of this, and this integral will be something that we can just read off. Okay, so all of the old stuff is still around. And then we have two of these, and we need to make sure that it's two of the whole thing. So u times v is t e to the t minus the integral of e to the t dt. So this is e to the t squared minus 2t e to the t plus 2. And now the integral of e to the t is just e to the t plus our constant. And that's it. Okay, so something that we learned is that sometimes you must use integration by parts multiple times. And then in the example above, we learned, so up here we learned that initially you may not really see a product, but we just use the product 1 times natural log of x, and that actually helped us out in this case. So here and in other times, the product might be slightly hidden. So that's something to look out for as well. So here we have an integral, and this time we've got a definite integral. So we have a starting and stopping point, and whatever our answer is, it's going to be some sort of number in here. This is a great one to stop the video and try this on your own. In the book Why We Remember by Charan Ranganath, the author writes, lasting benefits come from error-driven learning, during which we are not always going to be successful. We learn and retain more from the struggle of pushing ourselves to the edges of our knowledge than we do by memorizing and regurgitating on command. Perhaps instead of rewarding success, we should normalize mistakes and failures and incentivize constant improvement. So the point I want to make is that you're going to learn better as you kind of struggle through problems. We've talked about this before, but I really encourage you to attempt this problem before you see me do it. Okay, so at this point you have attempted the problem, you have a solution, or at least you've begun choosing what your u and dv are. And so this is kind of the key moment in the problem, is deciding what u and dv should be. And we want something that, for dv, that I can kind of mentally take an antiderivative of. Natural log of x is not a great choice because I can't mentally take the antiderivative of that. But something like 1 over x squared, I can pretty easily take an antiderivative of. And importantly, it'll be some power of x. And then if I let u equal a natural log of x, the derivative of that is 1 over x, so that when I go to integrate, I actually am ending up with just some power of x, and that's really helpful. That's easy to integrate. So this is probably the way I want to go, is to let u equal natural log of x and dv equals 1 over x squared. This -2, I'm just going to pull out so I don't have to worry about it, and then we'll stick it in at the end. Okay, so we're choosing for dv to be 1 over x squared dx, and we'll let u be natural log of x. Then the derivative of natural log of x is 1 over x, and we'll stick the dx right there. And then the antiderivative of this, so this is like an x to the -2, which means the antiderivative would be a higher power, so that would be like an x to the -1. We probably need a negative in front of it for it to work out right. The derivative of this should be this, and it is. So we're all set. Okay, so we can go ahead and find this integral. It'll equal u times v. Well, first of all, we got to stick the -2 out front, because we just pulled that out, so we don't have to deal with it. And then we've got natural log of x over x, and there's a negative, minus the integral of, oh, I should say, because this is a definite integral, this is going to be, this is going to be evaluated from 1 to e. minus the integral from 1 to e of v times du. And that will be negative 1 over x from the v times 1 over x from the du dx. So this is negative 2. We can go ahead and evaluate this right here. So we've got a negative natural log of e. That's just a negative 1 over e. So that's negative 1 over e minus, now we'll plug in the 1, negative natural log of 1, that's 0. Natural log of 1 is just 0 over 1 is 0. So that's that first part. And now we've got the integral from 1 to e of negative 1 over x squared dx. So I keep plugging along. I've got negative 2 times negative 1 over e minus, okay, the antiderivative of negative 1 over x squared is going to be one higher power, which is x to the negative 1. So that is x to the minus 1. And we have a negative there, so that works out perfectly. So it looks like this is the antiderivative we were looking for. And we're going to evaluate that from 1 to e. Let's see, get all my parentheses right. So I have negative 2, probably have too many parentheses, negative 1 over e minus, okay, now I start evaluating this. I've got e to the negative 1, which is 1 over e, minus 1 to the negative 1, which is 1. And that will be negative 2. Let's see, we have a negative 1 over e minus another 1 over e. So I've got two of those, negative 2 over e plus 1. This is going to be 4 over e if I just distribute, minus 2. I could leave it like that, or the decimal approximation is negative 0.52848. So hopefully you got something that looks like that. This is the solution to this problem. More importantly is, how did you do as you were choosing your u's and v's? And were you able to pick the right u and the right dv? This next example brings up a new scenario. Here we want the integral of e to the 2 theta times sine of 3 theta. So we definitely have a product going on here. The new thing, and sort of the difficult thing, is integrating e to a power, just you keep getting e over and over again. And integrating sine, you'll go to cosine, but then back to sine, to cosine, and so this also has a sort of repeating pattern. Neither of these factors in the product will start becoming simpler or start disappearing. They both stay very present. And so we're going to attempt integration by parts, but we're going to see that we're going to solve the problem in a new way. So here, again, we need to choose our u and dv, and this time it actually doesn't matter which is which, either the e to the 2 theta or the sine of 3 theta. We're going to see that neither of them really will become simpler. So let's say that u is e to the 2 theta, and then dv will be sine of 3 theta d theta, and then we'll go ahead and do the rest of it like we usually do. Du will be 2e to the 2 theta, and then v, we do a sort of anti-differentiation here, and so that will become, it will be a negative cosine of 3 theta, but thinking backwards through the chain rule, we will need a 1/3 right here. And we'll just double check this. If we took the derivative of this, it would be sine of 3 theta times 3, and this negative 3 will ensure that we have the 1 in front of the sign that we need. Okay, so we're all good. Now we can set up the results of this integration by parts. So it will be u times v, so that's a negative 1/3 e to the 2 theta times cosine 3 theta. So that's the first part of integration by parts, just multiplying these guys together. And then we will take a negative, the integral of these guys here, the v du. And that will be, let's see, the coefficients will be, we have a 2 and a negative 1/3, so that'll turn into plus 2/3. And we have an e to the 2 theta cos of 3 theta d theta. Now at this point we'd hoped that this integral would have become easier than the original integral, but it's really not. It's almost equally difficult. So what we're going to do from here is we are going to do integration by parts again. Why? You know, you might say, well, you're just going to get in this vicious cycle of nothing ever going away. But you can kind of see that in the next integration by parts, and we will do it, you'll see that we're going to end up with an integral that looks something like this in part of our solution. And this is actually the original integral. And that pops up again. It's the only integral left. And we're going to then not even solve this integral directly, but do some algebra to find the solution to this original integral. Okay, so the important thing here is we're going to do integration by parts again right here. So integration by parts, again, we have to pick our u and our dv. U, we'll just let that be, it's not a big enough box. We'll let u be e to the 2 theta again, and dv, we'll let that be the rest of it, cosine of 3 theta d theta. And then du equals 2 e to the 2 theta d theta. And v, we do a little bit of anti-differentiation here. We're going to go backwards. And so this will be, it'll be a sine 3 theta, but we'll need a 1/3 out here to make sure that we get the coefficient of 1 for this term. So let's just double check that. The derivative of this would be cosine 3 theta times 3, and then we multiply by the 1/3 and we get a coefficient of 1. Okay, so this looks good. Now we're going to put everything together. We still have this. We have 2/3 of whatever this integration by parts combination will be. I'm going to do something I haven't done a lot before. I'm actually going to rewrite the original problem, and you'll see why this is important. E to the 2 theta sine of 3 theta. That's the original problem, will equal our negative 1/3 e to the 2 theta cos of 3 theta plus 2/3. And now instead of this integral, we're going to do our combination of integration by parts. It'll be the uv minus the integral of v du. So uv will be 1/3 e to the 2 pi sine 3 theta minus the integral of v du, which is 2/3, just from this 2 here and this 1/3 here. And then we have an e2 theta sine of 3 theta d theta. So e2 theta sine of 3 theta d theta. And that's what our problem looks like right now. It's not that elegant or beautiful, but this is the original problem. This was a piece of the original integration by parts, and now we are doing a second integration by parts. And so this is what we want to evaluate. Everything is good, but we have this new integral here that we really can't evaluate either. But in fact, we notice something very important. This right here is actually the original integral. And because of that, we're going to use algebra at this point. We are not going to evaluate this integral directly, but you can see that we have one of these guys here, and we have 2/3 times negative 2/3, a negative 4/9 of the same exact expression over here. So we're going to take this, we're going to add 4/9 of that expression to both sides, so that will bring it over here. So we have e to the 2 pi sine of 3 theta d theta. And we have one of them from the original left side, and now I'm going to add 4/9 of them from this side, the right side of the equation. So we had one right here, and we had 4/9 of that same exact expression on the right side. And so we can combine those expressions. These are identical terms, objects, integrands, and so I can combine them, and this becomes 1 plus 4/9, that's like 9/9 plus 4/9, and so we get 13/9 of these. The important thing is that integral has become combined, and it's equal to whatever's left on the right side, negative 1/3 e to the 2 theta, cosine of 3 theta. And then we have what's left here, distributing this to just this part here. We have 2/9 e to the 2 theta sine 3 theta. Now the only thing left to do really is to multiply both sides by 9/13. Then it all goes away over here, and we'll multiply this by 9/13 over here, everything. And then you can see that we have an expression for what that integral is, and there's no integrals over here. It's just a bunch of terms that is equal to this integral. So we've essentially solved for the integral. We've done it by using integration by parts twice, but never directly evaluating an integral, just using some algebra. The lucky turn that we had was as we were going through integration by parts, this was the essential piece that we ended up with an integrand that matched our original integrand. This happens because you have two parts of your product, both of them getting into a repeating pattern. They're not changed. I mean, this one changed, but they're changing, but they're also in this cycle of returning to what they were. Okay, so let's finish off the problem. We're going to multiply both sides by 9/13. So we get the integral of e to the 2 theta sine of 3 theta d theta. Don't need that. Equals, okay, 9/13 times -1/3 will be -3/13 e to the 2 theta cosine of 3 theta. And 2/9 times 9/13 will be 2/13 e to the 2 theta sine of 3 theta. Okay, so this is, oh, importantly, this is the only opportunity, or the first opportunity we have to add our constant, and so we'll do that. And this is it. We found that the integral that they asked us to find is all of this. Okay, so I just want to think through exactly what happened in this problem. We had pieces that were never going to become simpler. These were the pieces that we were not going to end up with an integral that was simpler. But as we did integration by parts, and we actually did it 2 times, we got an integrand that matched the original. This was key to being able to solve this problem, that we were able to match the original integral, and we then used algebra. We had an integral here that matched the original integral here. That was because sine turns into cosine and then turns back into sine, and that's what enabled that to happen. So here were the 2 integrals that matched, and we never in the whole problem actually integrated directly. We just combined the integrals that matched, knowing that that was the one we were looking for. Everything that was left behind was integral free, and so then we were able to solve for that original integral. This is our next example. We're asked to find the integral of cosine of square root of x. It's, of course, this square root of x that's causing a little bit of difficulty. But we're also given a hint to use a substitution. And so this problem is actually going to involve substitution as well as integration by parts, but we're going to start by trying to use some sort of substitution. And the most obvious substitution to try is to let our variable equal the square root of x. That would simplify at least that part of the variable. So this will be the substitution part. We're going to let u equal square root of x. But then we have to also decide what du is, and that would be 1/2 x to the minus 1/2, or 1/2 square root of x dx. At first that seems like a little bit of a problem because we don't have this thing in the integral. But what we're going to do here is say that du, let's take the 2 times square root of x over, multiply both sides by 2 square root of x equals dx. This is kind of weird because we have a bunch of x's and u's all in the same equation. But remembering that square root of x is just u, we could say that 2u du equals dx. And this is what we're going to use for dx. So this is what dx equals. This is what the square root of x equals. And so we're going to transfer everything into u's at this point. So actually, I encourage you at this point to stop. Rewrite this in terms of u's. You'll have a cosine of u, and then write what dx is. You'll get an integral that you'll pretty quickly see it can be solved quickly by integration by parts. So try to take it from here. So we've already done the substitution. You go ahead and try the integration by parts all on your own after you make this substitution for square root of x and for dx. So go ahead and just pause the video and do the work in your notebook or paper, whatever. Okay, so at this point you've put the u's in for the substitution, and you've done a bunch of work on integration by parts, and you probably have come up with a solution. Let's see if we get the same thing. Okay, so first let's take care of the substitution. When we substitute it, we're going to have an integral of cosine of not square root of x, but u now, and dx is equal to 2u du. So we have to put this whole thing in for dx. So we'll move this guy over a little bit, and we have, well, let's just put the 2 outside actually. 2 times u and a du. Okay, so this is how the substitution should have happened, cosine of u now, and then the dx is equal to 2u du, so 2u du is what the dx gets replaced by. This integral, now that we've seen some integration by parts, looks like it's really a nice one for integration by parts. This is the part that will eventually just go away. This is the part that it's easy to find an antiderivative of. So the u that we want is actually just u. And then the derivative of that will be du. And the dv will be the cos of u du. And the antiderivative of that will be sine of u. Okay, so we now have all of our pieces for our integration by parts. And we know that this integral is equal to the product of this minus the integral of these guys. And that's awesome because the integral of sine u du is a really easy one to evaluate. So we'll be able to do that. And then we'll stick everything back in terms of x's. Okay, so this equals 2 times u times sine of u minus the integral of sine of u du. And so that's 2u sine u minus 2 times, the integral of sine u is cosine of u plus a constant. And now we'll stick everything back in terms of square root of x. 2 square root of x sine square root of x plus 2 cosine square root of x plus c. And this is the integral. One thing we learned in this example is that there are times when integration by parts and that u substitution method are both used in the same problem. We're going to end with these two examples and go ahead and try them on your own. And maybe the biggest hint I can give you is actually neither one of them require integration by parts. So pause the video and try to evaluate each of these integrals. And because they're definite integrals, you should end up with just a number at the end of each one. Okay, so you've had a chance to try each of these problems on your own. You've probably solved them. So this first one here, I do notice that the derivative of this is really close to this. It's not quite the same thing, but it's pretty close and it's going to be usable. So this is actually going to be just a u substitution. And I see that if I say let u equal e to the 2t plus 2t, then du equals 2e to the 2t plus 2 dt. And it's not quite, so this is going to turn into u. And this is not exactly this, but you probably see that it's just, this is just a multiple of this. So we can pull that 2 out. And we could say, we'll pull the 2 out and then take it over to the other side. So 1/2 du equals e to the 2t plus 1 dt. So we have e to the 2t plus 1 dt in our integral. And so we can substitute it for this now. And the only thing to really keep track of at this point, so we have a u down there and a 1/2 du. Actually, I'm going to write it like this. So the only thing to keep track of now is what happens to these limits of integration. And these were when t equaled 1 and t equaled 0, but now we're working in u's. So we'll go ahead and just translate everything into a u. So if t equals 1, that's e to the 2 plus 2. So I'm going to take this, instead of t equals 1, u is going to be e squared plus 2. And if t equals 0, then that's e to the 0, which is 1 plus 0. So this just becomes 1 here. So we'll erase that. Okay, so this is an awesome integral to integrate because we have the integral of 1 over u. The antiderivative of that is natural log of u. And we have a 1/2 out front. And our limits of integration are 1 to e squared plus 2. So we have 1/2 natural log of e squared plus 2 minus natural log of 1. And natural log of 1 is just 0. So this will equal 1/2 natural log of e squared plus 2. And if you want to get a decimal approximation, that is about 1.1198, I think. So the real key to this problem was this u substitution and recognizing that even though du wasn't exactly what was sitting there, it was going to be pretty close. It was just a multiple of what was left over. Okay, this next example is going to turn out to be even easier than that. We don't even need a u substitution. The thing that we're trying to integrate here can actually be simplified quite a bit. And so that's a thing that we always want to look for in any integration is, can we simplify what we need to integrate before we even begin? And this we can split up into two fractions, which make it just a reverse power rule. We don't even need a u substitution really. So we'll say this is equal to the integral from 1 to 2 of x third over x fifths. So that's 1 over x squared dx. That's just by taking this fraction. So x thirds over x fifths becomes 1 over x squared. And then I'm going to do the same thing and use write this fraction separately also. So that will be from 1 to 2 of 6, x to the 6th over x to the 5th is just x dx. These are awesome integrals to evaluate. The first one is just going to be a negative x to the minus 1. And then plus, let's see, 3x squared should do the other one. And we can just evaluate both of these with these limits of integration. And that's negative 2 to the negative 1, so that's negative 1/2. Plus 3 times 4 is 12, minus, and now we'll plug in this guy, negative 1 to the negative 1, and that's just negative 1, plus 3 times 1, or 3. So this will be, let's see, negative 1/2 plus 24 halves plus 2 halves minus 6 halves. We've got 26 minus 6 is 20, so how about 19 halves? Or 9.5 for our solution. So let's just think about what that means. We said that this integral is equal to the number 9.5. So if this were a function, the area between this function and the x-axis from 1 to 2 should be 9.5. Let's just do a quick double check on Desmos that sounds reasonable. Okay, so here we have the function that we were integrating. Here's a picture of the graph of that function, and we're going to say let y be less than or equal to that function, and we'll let 0 be less than or equal to y, and we're just going to go from x is between 1 and 2. And so this is really the area that we're calculating when we take that integral from 1 to 2 of this function. And it looks like this height right here would be about 7 times the width 1, that's 7 units. And then we have a little bit more than 5. This is not a straight line here, but it's approximately, that would be an area of about 2.5, pretty close. So it seems very reasonable that this area, this green area, would be 9.5, the 7 plus the 2.5. And that's what we calculated for that integral from 1 to 2. So this number does check out for this integral. So let's think of some of the things we saw as we did a lot of integration by parts examples. As we did integration by parts, we were just essentially reversing the product rule, and we were hoping that this integral that we manufactured or derived would be simpler than the one that we were given to do. From this example, we learned that the product that we're usually looking for in integration by parts might be slightly hidden. We used u equals natural log of x, and dv was just dx, and it actually worked out that this could be evaluated with integration by parts then. In this example, we learned that sometimes you must use integration by parts multiple times. This e to the t was just going to kind of stick around permanently, but this t squared would go to t and then to 1, and that second time is what made it eventually able to complete the integration by parts. This example was pretty ripe for integration by parts because we had this obvious product here, but neither one of these is ever really going to simplify. The e to the 2 theta is going to stick around indefinitely, and the sine is just going to alternate between sine and cosine. So in this example, we learned that we had pieces that were never going to become simpler, but as we did integration by parts, we went through it twice, we did get an integrand that matched this original integrand. And once we did that, we could use just some algebra to solve for this integral. We never actually directly solved an integral, we just used some algebra to collect some like terms, some like integrals. And then this was a good example. We had to actually do a use substitution before we did integration by parts. So some examples are going to require a couple different methods.